Welcome to our penultimate lesson. This lesson will continue talking about linear systems of ordinary differential equations. We'll start by talking about homogeneous linear systems with constant coefficients. That's the key theory. We'll extend this to what happens if we have complex eigenvalues. And then in the final section today, I'm going to introduce the concept of fundamental matrices. This is a typo. This should be section 5.3. And at the top, it should always be section 5.3. Consider x prime is equal to ax, where A is a square n by n constant matrix. So we have a vector prime is equal to a matrix multiplied by a vector. Now, if n was equal to 1, we would just have dx dt is equal to ax. First order linear equation, also a separable equation, and we know how to solve this. This is one of the first ones that we looked at. We know that the general solution is a constant multiplied by an exponential function. And then we're thinking for our general system of n variables and n equations, maybe it's always an exponential function in there. We wouldn't have a constant because now we're dealing with vectors, but maybe the solutions always look like a vector multiplied by an exponential function. We don't know the number r yet. We don't know if this is going to be real or complex, so let's just say some complex number r. And the vector, we don't know anything about this, so let's just say it's a vector of complex numbers. But what do we get if we start with the solution of vector? This is the Greek letter xi, multiplied by e to the power rt. If we put this in the equation, then on the left side, we differentiate e to the power rt to get r e to the power rt. And on the right side, we're going to get capital A xi e to the power rt. E to the power rt is always non-zero, so these we could cancel out. We must have that r xi is equal to a xi. Or rearrange this to put everything on the left. We must have that a minus ri xi is equal to 0. And this equation looks familiar to everybody that studied linear algebra. Everybody that studied linear algebra, including all of those who revised your linear algebra notes last night, know straight away that this is the equation for an eigenvalue and an eigenvector of A. So the idea is to solve a linear system like this. Step 1, find the eigenvalues. Step 2, find the eigenvectors. And then the solutions are going to be eigenvector multiplied by e to the power eigenvalue t. Let's look at an example. Solve x prime is equal to 1141x. First, we're going to find the eigenvalues, then we're going to find the eigenvectors, and then our functions are going to be eigenvector e to the power eigenvalue t. I trust that you know how to find eigenvalues. This example, I'm going to go through the details, but future examples, I'm just going to be telling you the eigenvalues and the eigenvectors. How do we find eigenvalues? We always start with the determinant of a minus ri is equal to 0. Or equivalently, we can swap the places of a and ri, of course, because multiplying a determinant by -1 sometimes can multiply the determinant by either 1 or -1. But multiplying 0 by 1 or minus 1 still gives 0. So it doesn't matter if it's a first and ri second or ri first and a second. So we start with this equation, and we find that we must have 0 is equal to r squared minus 2r minus 3, which we could factorize to r plus 1, r minus 3. So the eigenvalues must be 3 and minus 1. Step 2 is to find the eigenvectors. First, we'll use the eigenvalue 3. We put this into our equation. The 0 vector must be a minus 3i xi. And that tells us that we need to have minus 2 xi1 plus xi2 is equal to 0. We can take any vector which satisfies this equation. So I'm going to choose the vector 1, 2. Then we need the second eigenvector. We look at the second eigenvalue. We're going to look at minus 1. Put this into our formula, and we need to have 2 xi1 plus xi2 is equal to 0. Again, we can take any vector which satisfies this equation. So I choose a nice easy one. I'm going to choose 1 minus 2. As soon as we know our eigenvalues and our eigenvectors, we know our two solutions. Because our solutions are eigenvector e to the power eigenvalue t. That's 1, 2, e to the power 3t. And for the second function, same idea, eigenvector e to the power eigenvalue t. 1 minus 2, e to the power minus t. But are these two solutions linearly independent? To answer this, we need to calculate the Wronskian of these two functions. Before we calculate the Wronskian, let's write them slightly differently. Let's take the exponential function inside the vector. So the first one becomes e3t, 2e3t, and the second function becomes e to the minus t minus 2e to the minus t. And then the Wronskian is the determinant of the matrix, where the first column is the first solution and the second column is the second solution. And when we calculate this determinant, we find that we get something which is always non-zero. So the answer is yes. These two solutions are linearly independent. That tells us that they form a fundamental set of solutions, and then we can write down the general solution. The general solution is constant multiplied by the first function plus constant multiplied by the second function. Now let's do an initial value problem. Solve x prime is equal to 8 minus 161x with the initial condition x of 0 is equal to 1 minus 2. I'm not going to be calculating the eigenvalues and the eigenvectors each time. From now on, in most of the examples, I'm just going to be telling you the eigenvalues and the eigenvectors, and I'm going to be trusting that you know how to calculate these yourself. The eigenvalues of this matrix are 7 and 2, and the corresponding eigenvectors are 1, 1 and 1, 6. As soon as we know the eigenvalues and the eigenvectors, we can write down the general solution to the differential equation. Constant, C1, eigenvector, e to the power eigenvalue t, plus constant eigenvector, e to the power eigenvalue t. There's one step left to finish this question. We need to find the correct constants C1 and C2, which satisfy the initial condition. We want to have x of 0 is equal to 1 minus 2. So I'm starting with this. I'm starting with x of 0 is 1 minus 2. And I'm going to replace every t by 0. I get c1 plus c2, c1 plus 6c2. That gives us a linear system of two equations. c1 plus c2 must be equal to 1. c1 plus 6c2 must be equal to minus 2. From linear algebra, you know how to solve linear systems like this. So I can just tell you the solution. We need to have that c1 is 8 over 5 and c2 is minus 3 over 5. And that's all we need to write down the solution to this initial value problem. Put everything in. The solution must be 8 over 5, 1 e to the power 70, minus 3 over 5, 6 e to the power 2t. Another one. Solve x prime is equal to minus 3 root 2 minus 2x. We need the eigenvalues and the eigenvectors. The eigenvalues are minus 1 and minus 4, and corresponding eigenvectors we could take 1 root 2 and minus root 2, 1. So we can write down the solution. Constant eigenvector e to the power eigenvalue t plus constant eigenvector e to the power eigenvalue t. And that's it. That's all we need to do. Now, so far, all of our eigenvalues have been real numbers and they've all been different. In fact, there's 3 possibilities for the eigenvalues of A. Case 1, we might have that all of these eigenvalues are real and different. This is the case we've been looking at so far in these examples, the easiest case. Case 2, maybe some eigenvalues occur in complex conjugate pairs. We'll look at that later today. And it's also possible that some of the eigenvalues are repeated. For the easiest case, if all of the eigenvalues are real and different, then that means that the eigenvectors are linearly independent. And if the eigenvectors are linearly independent, then we can use that to prove that the Wronskian is always non-zero. In other words, as long as the eigenvalues are real and different, we always have a fundamental set of solutions. If some of the eigenvalues are repeated, but, and this is the key point here, but there are still n linearly independent eigenvectors, then this is also true. We can use the same method and we find a fundamental set of solutions, which I will show in this example. Solve x prime is equal to 0, 1, 1, 1, 0, 1, 1, 1, 0, x. The eigenvalues and the eigenvectors are shown here. You will note that now I have repeated eigenvalue. I have minus 1 and minus 1. But I have 2 linearly independent eigenvectors. In this case, we can carry on using the same method. We can write down 3 solutions just using the method I've shown before, and these 3 solutions will be linearly independent. In other words, these 3 solutions form a fundamental set of solutions. I'll leave it for you to check that the Wronskian of these 3 functions is non-zero. In other words, I'm leaving it for you to check that they really do form a fundamental set of solutions. And therefore, we can write down the general solution to the differential equation. Just constants, and then solution plus constant solution plus constant solution. That's what happens if we have repeated eigenvalues, but we still have n linearly independent eigenvectors. Sometimes that's not true. Sometimes we have repeated eigenvalues and we don't have enough linearly independent eigenvectors. For that case, we're going to study next week. Next, I want to study the case where we have complex eigenvalues. This should be section 5.4. Again, we're going to be considering a homogeneous linear system with constant coefficients. In other words, we're going to be looking at x prime is equal to ax. That means, and I'm just reminding you, that means x1 prime, x2 prime, etc. is equal to this square matrix multiplied by x1, x2 up to xn. And this is another way of writing this linear system. x1 prime is equal to a11 x1 plus a12 x2, etc. Instead of writing this complicated thing, we like to write x prime is equal to capital AX. Now, if we have complex eigenvalues of our matrix, then they must occur in complex conjugate pairs. So if lambda plus I mu is an eigenvalue, where lambda and mu are real numbers, then lambda minus I mu is also an eigenvalue of A. And we can say the same thing for eigenvectors. If xi1 is an eigenvector corresponding to R1, then the complex conjugate of xi1 is an eigenvector corresponding to R2. So two solutions of our linear system are xi1 e to the power r1t and complex conjugate of xi1 e to the power complex conjugate of r1t. But these are complex valued functions. These are functions which map from the real numbers to Cn. They map from R because the t we're going to put into the function is a real number, but we're being given a complex vector. And we don't want this. We want solutions which map from the real numbers to Rn. So what are we going to do? We had a similar problem in chapter 3. We're going to use the same idea here. Now, let's suppose R1 is lambda plus I mu, and let's suppose that xi1 is A plus IB, where lambda and mu are real numbers, and A and B are real vectors. Then we can write x1 like this. A plus IB, e to the power of lambda t, cos mu t plus I sine mu t. And let's rearrange this so that we move all of the real parts and separate from all of the complex parts. We can rearrange it like this. E to the lambda t, a cos mu t, minus b sine mu t, that's all of the real parts, plus I, e to the lambda t, a sine mu t plus b cos mu t. In orange, we have all of the complex parts. And these functions, the green function, the orange functions, are the ones we want. I'm going to call these U and V. Now, these two functions are going to be linearly independent. They're going to solve the differential equation, and they're going to have the same span as x1 and x2. That means that instead of using x1 and x2 in our fundamental set of solutions, we can use u and v instead. So that's the theory. Let's do an example. Solve x prime is equal to minus a half 1, minus 1 minus a half x. We need the eigenvalues. I'll leave this calculation for you to double check. Please check that this is correct and that the eigenvalues are -1/2 plus or minus I. So R1 we're going to call -1/2 plus I, and R2 is equal to -1/2 minus I. We don't need R2, we're going to use R1. So forget about R2, we're just going to be using R1. We need an eigenvector corresponding to R1. So we do our calculation. We find that we must have that minus I xi1 plus xi2 is equal to 0, and minus xi1 minus I xi2 is equal to 0. These two equations are the same. If you remember that I squared is equal to -1. The top equation is just the bottom equation multiplied by I. We can choose any vector which satisfies these equations. I like easy vectors, easy functions, so I'm going to choose the vector 1i. Now, if we needed it, straight away we could write down that xi2 is the complex conjugate of xi1. Complex conjugate of 1 is 1. Complex conjugate of I is minus I. So xi2 must be 1 minus I. But we don't need this. We can forget about this slide. This is not necessary. We need to write down x1. x1 is xi1 e to the power r1t. That's 1i e to the power minus t over 2 cos t plus I sine t. And I want to rearrange this so that I'm separating all of the real terms from the imaginary terms. And I can do that like this. The real terms are e to the power minus t over 2, cos t minus sine t. And the imaginary terms are e to the power minus t over 2, sine t cos t. These are the two functions that we want. The green function will be called u, and the orange function will be called v. But are they linearly independent? On a previous slide, I said that they would always be linearly independent. Let's just check that for this in this case. We calculate the Wronskian of these two functions. The first column is u, and the second column is v. And when we calculate this determinant, we find that we get e to the power minus t, which is always non-zero. So the answer is yes. These two functions are linearly independent. This means that they form a fundamental set of solutions. Now that we have our fundamental set of solutions, we can write down the general solution to our differential equation. C1, e to the power minus t over 2, and then the vector cos t minus sine t, plus C2, e to the power minus t over 2, and then the vector sine t cos t. So let's just recap our method. To solve x prime is equal to ax, step 1, find the eigenvalues, and step 2, find the eigenvectors. If we have a real eigenvalue, then the function that we want is eigenvector e to the power eigenvalue t. If we have complex eigenvalues, it's a little bit more complex. We need to rearrange our eigenvector e to the power eigenvalue t function to a real valued function plus I multiplied by a real valued function. And then instead of using two functions, we use the green function and the orange function. The next example is about this electrical circuit. We have two resistors, one inductor and one capacitor. And the voltage and current in this electrical circuit is described by I prime is equal to minus I minus V. V prime is equal to 2I minus V, where I is the current through the inductor and V is the voltage drop across the capacitor. Why is that true? I'm just going to say ask an electrical engineer. I'm not going to dwell on why that's true. For this maths course, just assume that this is correct. I want to suppose that at time t equal to 0, the current is 2 amperes and the voltage drop is 2 volts. Find I and V as functions of time. So in other words, we need to solve an initial value problem. We have that the derivative of our IV vector is minus 1, minus 1, 2, minus 1, multiplied by our vector IV, and we want to use the initial condition IV at time 0 is equal to 2, 2. So we need the eigenvalues and the eigenvectors. Here they are. I'm just going to tell you that the eigenvalues are minus 1 plus I root 2 and minus 1 minus I root 2. I'll leave that for you to check. And the corresponding eigenvectors are 1 minus I root 2 and 1 I root 2. Again, I leave that for you to check. We don't need both of these. We only need one eigenvalue and one eigenvector. We could choose R1 or we could choose R2. I'm going to use R1. So forget about R2 and forget about Xi2. We don't need these. We're just going to use R1 and Xi1. We take x1, that's Xi1 e to the power R1t, and rearrange it. And we find that we get e to the power minus t cos root 2t, root 2 sine root 2t, plus I, e to the power minus t, sine root 2t, minus root 2 cos root 2t, which I leave for you to check at a later time. These are the two functions that we want. This green function will be u, and this orange function will be v. As soon as we know these, we can write down the general solution to the differential equation. Constant multiplied by the green function plus constant multiplied by the orange function. All that's left is to use the initial condition to calculate C1 and C2. Because cos of 0 is 1 and sine of 0 is 0, we find that we must have that C1 is 2 and C2 is equal to minus root 2. So our solution must look like this. Now, there's one more step. The question didn't ask us for a vector solution. The question asked us for two functions, I of t and v of t. So our answer should be what the question is asking for. I of t, we can read off from the top line, is 2e to the power minus t cos root 2t minus root 2 e to the power minus t sine root 2t. And from the bottom line, we can read that v is 2 root 2t, root 2 e to the power minus t sine root 2t plus 2 e to the power minus t cos root 2t. For the next example, I want to go back to talking about two masses which are joined together and joined together joined to a left and a right wall with springs. I want to suppose that the mass of the left block is 2 kilograms, the mass of the right block is 9/4 kilograms, and I want to suppose that the spring constants are 1 Newton per meter, 3 newtons per meter, and 15/4 newtons per meter. I want to suppose that the top pitch is the base position, where you can say that x1 and x2 are 0, and then as these blocks oscillate left and right, x1 and x2 will be their displacements to the right. I've generated an animated GIF for this picture, which you can view at the website I've listed at the bottom. Or you can look in the content section, the course content section of OLearn, and you'll see that I've also put the animated figure just there. Now, for this dynamical system, find x1 and x2. Let's talk first about the forces on the blocks. We're going to suppose that the only forces on the blocks are the forces generated by the springs. Now, first of all, let's look at the left block and let's look at the left spring. As this block moves to the right, the left spring is going to be wanting to pull it back to the left, back to its base position. And because the spring constant is 1, the force is going to be spring constant multiplied by the displacement. That's 1 multiplied by x1. There's a second spring attached to the left block. The middle spring is attached to the left block. And this spring is going to be pulling the block to the right. The spring constant is now 3. How much is the spring stretched by? It's stretched by x2 minus x1. So the force that the middle spring applies to the left block will be 3 multiplied by x2 minus x1. We can do the same thing for the right-hand block. This is going to pull the right-hand block to the left with force 3x2 minus x1. And then finally, the right-hand spring is attached to the right-hand block. As the block moves to the right, this spring is going to become compressed and it's going to be wanting to push backwards. So as we move to the right, this force is going to be pushing to the left. It's going to be pushing to the left by 15/4 x2. Because the spring constant is 15/4, and the spring becomes compressed x2 meters. So these are the forces. We know that mass times acceleration is equal to force. So looking at the left block, first of all, the mass is 2, and the acceleration will be the second derivative of x1. Add up the forces, remembering that moving to the right is the positive direction. 1x1 is pointing to the negative direction, so it becomes minus x1. 3x2 minus x1 is moving to the positive direction, so that becomes plus 3x2 minus x1. And we can do the same thing for the right-hand block. Mass times acceleration is 9/4 d squared x2 dt squared. And the force will be minus 3x2 minus x1, because it's pointing to the left, and then minus 15/4 x2, again, because that's pointing to the left. Let's tidy this up a little bit. That gives us a system of 2 second-order linear ordinary differential equations. We haven't studied a system of second-order equations. We've been studying systems of first-order equations. But we have seen how to change second-order equations into two first-order equations. We're going to use that technique again. We're going to introduce some new variables. First of all, y1 and y2 will be the old variables. y1 will be the same as x1, and y2 will be the same as x2. We also need derivatives of these. x1 prime I'm going to call y3, and x2 prime I'm going to call y4. Then, what do we have? x1 prime must be y3. x2 prime must be y4. x3 prime, differentiate this, that's x1 double prime. And from the equation at the top, that's a half minus x1 plus 3x2 minus 3x1, or that simplifies to minus 2y1 plus 3 over 2 y2. And then we can do the same thing for y4. y4 is x2 prime, so y4 prime is x2 double prime. From this equation, we can write to x2 double prime in terms of x1 and x2, or in terms of y1 and y2. We get 4 over 3 y1 minus 3 y2. Now we have a system of 4 first-order linear differential equations. And if we write that in terms of matrices, it looks like this. We know how to solve things like this. We need the eigenvalues and the eigenvectors. I'll tell you that the eigenvalues are I, minus I, 2I, and minus 2I. We don't need all 4 of these because we have none of us. We're going to be using R1 and R3. We don't need R2. Forget about R2. We don't need R4. Forget about R4. The corresponding eigenvectors, and I leave this for you to check, are 3, 2, 3i, 2i, and 3 minus 4, 6i, and minus 8i. I'm skipping through a lot of the details here. Using R1 and Xi1, we find a green function plus I multiplied by an orange function. Using R3 and Xi3, we find that we get a red function and a blue function. These 4 colored functions are the functions that we want for our fundamental set of solutions. And then the general solution is going to be C1u plus C2v plus C3w plus C4z. Or substituting everything in, the solution looks like this. Now, let's suppose that the above system has initial condition -1, 4, 1, 1. Sketch the graphs of y1 and y2. Remember, y1 is the same as x1. That's the displacement of the left-hand block. And y2 was the same as x2, the displacement of the right-hand block. Using the initial condition, we can calculate the constants, and we get this complicated function here. And then we can use this to sketch the graphs, which I've done with a computer. This is the graph of y1 or x1. This is how much the left-hand block moves. And this is the graph of y2 or x2, how the right-hand block moves. And I have an animated figure of this, which I'm trying to find. Here we go. Using these functions, which I showed in the previous slide, I was able to generate this animated figure. You can find this figure in the course content section of OLE. Now let's go back to the slides. You can find this animated GIF at this address. Now, today's lesson is quite a long lesson. Still have lots of slides still to go. I'm going to be more than an hour today. Before we start a new topic, this is a good place to take a break just to let you refresh your minds. So let's take a 10-minute break before we continue. Now let's continue. The third and final topic for today's lesson is the topic of fundamental matrices. This should be section 5.5. In this section, we're going to consider the homogeneous equation x prime is equal to ptx, where p is now an n by n matrix function. We're going to suppose that we know n linearly independent solutions to this differential equation. In other words, we're going to suppose that we have a fundamental set of solutions. And what we're going to do is we're going to write a matrix where the first column is the first solution, the second column is the second solution, and so on. This square n by n matrix is called a fundamental matrix of the linear system. And for this, I'm going to be using capital Xi. For example, write a fundamental matrix for x prime is equal to 1, 1, 4, 1, x. Now, let me remind you, we already know a fundamental set of solutions to this differential equation. We know that we have 1 to e to the power 3t and 1 minus 2 e to the power minus t. So we can write down a fundamental matrix like this. The first column is the first function, and the second column is the second function. And that's it. Now, back to the theory. The general solution to x prime is equal to ax we can write as a linear combination of the functions in the fundamental set of solutions. Or, there's a neater way to write this. We can write this as a fundamental matrix multiplied by a constant vector. And if we have an initial condition, let's say x at time t0 is the vector x0, replacing t by t0, we have that xi t0c is equal to x0. So that's two equations so far. xt is equal to xi tc, and xi t0c is equal to x0. But we have n linearly independent functions. Because they're linearly independent, that means that the fundamental matrix must be invertible. If it's invertible, then the right-hand equation we can change to being c is equal to xi inverse at time t0, x0. And then we can take this and we can substitute it into the first equation. In other words, we can write down that the solution to the initial value problem is xi at t, xi inverse at t0, x0. Here's a theorem. Suppose that xi is a fundamental matrix for x prime is equal to ptx. Then xi t solves effectively the same differential equation. It solves xi prime is equal to pt xi. And I'm going to leave this theorem for you to prove. One of the exercises in the lecture notes asks you to prove this. You should be able to prove this. We'll come back to that theorem later. We'll need that theorem later. Moving on to the next idea. It's possible to find a special fundamental matrix, which I'm going to call capital phi, which satisfies that phi at time t0 is the identity matrix. For this special fundamental matrix, I'm going to use the notation capital Phi. And for just any fundamental matrix, of which there are infinitely many, I'm going to be using the notation capital Xi. So phi for the special one and xi for any fundamental matrix. Go back to this one. Consider x prime is equal to 1141x. Find the special fundamental matrix which satisfies phi of 0 is equal to the identity matrix. Now we need to satisfy two initial conditions. In order to get that the first column is 1, 0, we need to satisfy the initial value problem where the initial condition is 1, 0. And to get that the second column is 0, 1, we're going to need to be solving an initial value problem with the initial condition 0, 1. We know the general solution to this differential equation. We just need to satisfy these two initial conditions. Let's do the green one first of all. In order to get 1, 0, we find that the constants we must have are half and half. So our green function is a half e to the power 3t plus a half e to the power minus t, and then e to the power 3t minus e to the power minus t. This is going to be the left column of our special fundamental matrix. And then we do the same for the right column. Now starting with the initial condition 0, 1, we find that the constants must be a quarter and minus a quarter. So now we have this orange function, a quarter e to the power 3t minus a quarter e to the power minus t, a half e to the power 3t plus a half e to the power minus t. This is going to be the right column of our special fundamental matrix. So here we are. Put it in. Left column is the green function, right column is the orange function. We have our special fundamental matrix. And you can just check, I'll leave it for you. Write down capital Phi at time 0. And you will find that we get 1, 0, 0. What is e to the power of a matrix multiplied by t? Now, let's go back all of the way back to chapter 1. The solution to x prime is equal to ax, x of 0 is x0, where small a is just a number. We know that the solution to this initial value problem is x0 e to the power 80. Or x0 exponential function of 80. And from first year calculus, we know that the Taylor series for the exponential function is 1 plus the infinite series from 1 to infinity, a to the power n, t to the power n over n factorial. We can use the same idea to define e to the power 80. Consider x prime is equal to capital AX, x of 0 is equal to x0. And we're going to define the exponential function of capital AT in almost exactly the same way. Sum from n is equal to 1 to infinity, a to the power n, t to the power n factorial. That's exactly what we had on the previous slide. The only difference here is instead of the number 1, just here, because we're doing matrices, instead of number 1, we have the identity matrix. So anytime you see exponential function of 80, it means I plus 80 plus a squared over t squared, a squared t squared over 2 factorial plus a cubed t cubed over 3 factorial plus etc. Now, what do we get if we differentiate this? I want to differentiate I plus the infinite series from 1 to infinity an tn over n factorial. Of course, the derivative of I is just 0 vector. Let's not worry about radii of convergences, etc. in this course, and let's just suppose that it's okay to take a derivative inside an infinite series. There's actually cases where this is not true, but for this one it does work. But don't worry about the details in this course. Let's suppose we can take the derivative inside the series, differentiate t to the power n. We get n t to the power n minus 1. The n cancels with the n at the bottom, and we get an t to the power n minus 1 divided by n minus 1 factorial. Separate out the first term first of all. N is equal to 1. Term will move out, and then we'll start the series at n equal to 2. And then I'm going to do a substitution. Every n minus 1, I'm going to replace by k. So instead of n minus 1 on the bottom, I get k factorial on the bottom. Instead of t to the power n minus 1, I get t to the power k, etc. Instead of starting the sum at n equal to 2, I'm going to be starting the sum at n equal to 1 because of the substitution. And I'm going to take one factor of a outside the bracket. So we get capital A multiplied by I plus the infinite sum, k is equal to 1 up to infinity, a to the power k, t to the power k over k factorial. But what is this in the brackets? This is just the exponential of 80. So using this definition, the derivative of the exponential of 80 is just a exponential of 80. Because of course it is. That's what we want it to be. That's why we use this definition. But that means that this function, exponential of 80, solves the derivative of exponential of 80 is equal to a exponential of 80, and the exponential of 80 at time t equal to 0 is equal to the identity matrix. But wait a minute, the special fundamental matrix also solves this. It also solves capital psi prime is equal to a capital psi. There's a typo here. This should be capital psi. And it solves capital psi of 0 is equal to the identity matrix. Because solutions of these initial value problems are unique, we must have that these two functions are the same. So the special fundamental matrix, as long as our initial time is 0, is the same as the exponential function of 80. So for example, if you had an exam question which said find exponential of 80, it's another way of saying find the special fundamental matrix. With the proviso, the key point here, that you're using initial time 0. So for example, let a be equal to 8 minus 161. Find the exponential of 80. In other words, find the special fundamental matrix which satisfies that capital phi at 0 is equal to the identity matrix. We've previously found the general solution to this differential equation. We need to satisfy the initial conditions 1, 0 and 0, 1. To satisfy 1, 0, we need the constant 6 over 5 and minus 1 over 5. So we get this green function. To satisfy x of 0 is equal to 0, 1, we have to have the constants minus 1 over 5 and 1 over 5. So we end up with this orange function. And then we can write down the answer to this question. The exponential of AT, or to say it another way, the special fundamental matrix which satisfies that capital phi of 0 is equal to the identity matrix, is this matrix where the left column is the green function and the right column is the orange function. Next idea, an idea we're going to be using in the next lesson. Let me remind you about diagonalizable matrices. If we have a diagonal matrix, that's a matrix where every element which is not on the main diagonal is 0. We can have any number that we want on the main diagonal. Then it's easy to calculate the exponential of this function because we just get e to the power r1t, e to the power r2t, etc. down the main diagonal, and 0 everywhere else. Now consider x prime is equal to ax for some square n by n constant matrix. And let me remind you how we diagonalize this matrix. If we have the eigenvectors of A, we write down the transition matrix capital T, where the first column is xi1, second column is xi2, etc. If the determinant of this matrix is non-zero, then T inverse exists, and T inverse AT gives us a diagonal matrix. In other words, as long as the determinant of T is not 0, we have a matrix which is diagonalizable. This should be revision for you from your linear algebra course. For example, diagonalize the matrix 1, 1, 4, 1. The eigenvalues are 3 and minus 1. The corresponding eigenvectors are 1, 2, and 1, minus 2. So T, first column is 1, 2, and the second column is 1, minus 2. We can write down T inverse, and we can write down D inverse, T inverse AT. We could multiply 3 matrices together if we wanted to, or we could just know that from that, we could just remember that we know from linear algebra that this must be the diagonal matrix where the numbers on the main diagonal are the eigenvalues. Now, x prime is equal to ax. The key idea in this section is we're going to define a new variable called y. And we're going to define it like this. We're going to say x is equal to ty, or saying this another way, y is equal to t inverse x. That's the key idea in this method of diagonalization, which we're going to be using next week. We're going to substitute this into our differential equation. Instead of x prime is equal to ax, we have ty prime is equal to aty, because we replace every x by ty. And then we can apply T inverse on the left side to both sides and get that y prime is equal to dy. We know a fundamental matrix for y prime is equal to dy. We know that this is exponential dt, and we can write down this straight away. It's the diagonal matrix where the elements on the main diagonal are e to the power r1t, e to the power r2t, etc. Therefore, a fundamental matrix for the equation that we started with, we can get by multiplying on the left by t. Because if you remember, x is equal to ty. If we know a fundamental matrix that we can use to find y, we can multiply on the left, and we can get a fundamental matrix which we can use to find x. So, for example, find a fundamental matrix for x prime is equal to 1141x. Let me remind you of the transition matrix. The key step is we're going to let y be equal to t inverse x. And then that gives us the easier differential equation, y prime is equal to 3, 0, 0, minus 1y. Straight away, we can write down a fundamental matrix for this equation. Instead of 3, we have e to the power 3t. Instead of minus 1, we have e to the power minus t on the main diagonal. And then to find a fundamental matrix for the equation that we want, we just multiply on the left by the transition matrix T. And we get e to the power 3t, e to the power minus t, 2 e to the power 3t, minus 2 e to the power minus t. And if you look back through your lecture notes or these slides, you'll see this is just what we had before. Next week, we're going to be using the same ideas. We're going to be using the ideas that to solve a complicated equation, we can make it easier using the substitution x is equal to ty. But that's enough for today's lesson. Next week, in the final lecture, we're going to cover the final 2 sections. Section 5.6, which I've called repeated eigenvalues, is actually should be called repeated eigenvalues where we don't have n linearly independent eigenvectors. But that's quite lengthy, so I've just called it repeated eigenvalues. And then in the final section, which is perhaps quite a tricky section, we're going to be studying non-homogeneous linear systems. And I would say section 5.7 is one of the hardest sections in this course. Are there any questions?